Well, good morning. It's 8:07, sorry we're late getting started, but my computer's been very slow booting, loading PowerPoint, and then Screencast-O-Matic. I've had to try numerous times to get it to open. So finally we're up and running, but I still have no students in the room. I'm the only one in here. This is Math 237, linear algebra, and like I said, it's after 8 in the morning. I can't think of any major announcements to give. Trying to get the current slide to come up. There it is. Okay, so I guess we'll pick up from where we left off last time. And it seems as if last time we finished 2.3, and I don't believe we got started at all in 2.4. So that's where we're starting today. So let's go from there. 2.4 is talking about elementary matrices. Now, I don't know how to approach this, but it is an important concept, at least theoretically. And I believe that practically, once you're doing things on a computer, perhaps this is a very useful concept. But for the stuff we do every day, that we've been doing, solving them by hand and stuff like this, yeah, theoretically it makes some sense and maybe gives more insight in how it works. And perhaps, well, I can't even imagine this, that, there's some other practical application. But in a lot of ways, I don't see any. I mean, after we do this section on elementary matrices, we may mention them a time or two again, and that's about it. But I hesitate to skip the section because they do make a deal of it. So I'll try to go through it rather quickly, but not too quickly so you can't follow what's going on. So elementary matrices and elementary row operations are very intricately connected, okay? That's exactly what an elementary matrix is. It's dealing with a single elementary row operation at a time. So back in section 1.2, way back, we introduced the 3 elementary row operations for matrices: exchanging 2 rows, multiplying a row by a non-zero constant, and adding a multiple of one row to another row. We've been doing it over and over and over, okay? So in this section, we'll see how to use matrix multiplication to perform those operations, okay? And again, I think from a computer viewpoint, programming viewpoint, perhaps this is useful, okay? I've not done that much programming with matrices. They have canned packages. I've used a little bit, and they work, and you don't really, as far as I know, even have to think about the elementary matrices behind it. But perhaps they were useful in doing it. Anyway, before we get started, there is a remark here. The identity matrix IN is elementary by this definition that we're about to give, okay? Because it can be obtained from multiplying itself by multiplying any of its rows by 1, okay? That's not a very useful remark in my mind, but it's there. I wanted to go over it. So here's the definition of an elementary matrix. And because not everybody's here, I don't know if everybody's got a book yet. Nobody's here. I don't know if anyone doesn't have a book yet, but in case you don't, here's the definition of an elementary matrix. First, let me get my pen set up. Okay. First, you have to have a square matrix. N by N matrix. Okay? Now this N by N matrix is an elementary matrix. Okay? An elementary matrix when it can be obtained. Sorry about my writing. The screen wobbles, and this pen is not very easy to write with, is obtained from the identity matrix okay, of that same size, by a single elementary row operation. Elementary row operation. Okay? It's a square matrix. It's an elementary matrix when it can be obtained by starting with the identity matrix. You know what that is. Okay? One's down the main diagonal, zeros everywhere else. And you start with that and then do a single elementary row operation on that identity matrix. And we just went over what they are. Exchange two rows, multiply one row by a non-zero constant, or add a multiple of one row to another row. Okay? Those are it. If you get an n by n matrix from that, and basically, after a while, you can look at them and tell whether it's an elementary matrix. It looks enough like an identity matrix that you can just about spot it right off the top. So, and remember, an identity matrix is an elementary matrix because you can multiply any row by itself, and you still got by one, and you still got the identity matrix. So that is, by definition, an elementary matrix. So, example 1 says, which of the following matrices are elementary? So let's see. Let's look at a few of these. The first one is 1, 0, 0, 0, 3, 0, 0, 0, 1. That an elementary matrix? I wish somebody were here. Of course it is. Why is it elementary matrix? You started with the identity matrix, which would have been a 1 where that 3 is, and multiply that row, the second row, by 3. One elementary row operation, that would have created this matrix, so therefore this is an elementary matrix. Here's B. 1, 0, 0, 0, 1, 0. Is that an elementary matrix? Absolutely not. Why not? The first thing it said about an elementary matrix, it has to be square. This is not square, this is rectangular. Finally, Nigel's here. Bing, 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 bing. We finally got a student in. Thank you. I feel sort of retarded talking to myself. Okay? Sorry about that. What's that? Oh, no problem. Well, when I got started, I'm on example 1, page 74, chapter 2, matrices, section 2.4, elementary matrices. And I guess I'll repeat some of this while the projector's lighting up. And I hate to say this because it probably just shows my lack of understanding of these things, but we do this section, and then seldom do we ever use elementary matrix again. I'm not saying they're not useful. I'm not sure why they make such a big deal about them. I think perhaps when you're doing computer programming to solve matrices, maybe then it makes sense. And here's, both of the Williams brothers are here. Okay. So the bottom part of the alphabet's doing quite well. The top part is not here yet. All right. We're doing elementary matrices, section 2.4 in chapter 2, matrices. And I've just written the definition or a shortened form of it. If you got your books, you'll see a better form for it in your book. I did a lot of shorthand. But we started off by reminding ourselves what our elementary row operations are. Can anyone tell me? The elementary row operations. Okay, yeah, this is one thing. It has to be a square matrix. But you can use elementary row operations on any matrix. What are those 3 elementary row operations? You can exchange any 2 rows. Multiply any row by a non-zero constant. Multiply any, yeah. A multiple of one row to another row, exactly, okay? And now, to be an elementary elementary matrix, it has to be a square matrix. Even though you can use your elementary row operations on any matrix, to have an elementary matrix, it has to be square. Now, what is an elementary matrix? You start with the identity matrix of that same size. So if it's n by n matrix, you're trying to determine if it's elementary, start with identity matrix of that size, and if you do a single elementary row operation on that identity matrix, that produces what they call an elementary matrix. Okay? So, we did this one. This is example 1A. Is that an elementary matrix? Yes. And what? What single row operation did you do on I? Say again? What elementary row operation? You just gave me the 3 elementary row operations. Which one of those did you do on the identity matrix to produce this matrix? Yes, you multiply the second row by non-zero constant 3. Exactly. You can only do one. This is this an elementary row? Elementary matrix. Say again? Why not? It's not square, exactly. It's a rectangular matrix, not a square matrix, okay? How about this one? This is C. 1, 0, 0, 0, 1, 0, and 0, 0, 0. Is that an elementary matrix? Why not? Yes, the only way you could get this from an identity matrix would be to multiply the third row by 0, but the rule of the elementary row operation says multiplying a row by non-zero constant. So this is not an elementary matrix. You're absolutely right. How about this one? This is D. 1, 0, 0, 0, 0, 1, 0, 1, 0. Is that an elementary matrix? Say again? Yes, why? Which elementary row operation did you do? Exchange the second and the third rows. Absolutely. How about this one? 1, 0, 2, 1. Is that an elementary matrix? Why? What elementary row operation did you do? Multiply the first row by 2 and add it to the second row. You're absolutely right. Okay, and F, this one. 1, 0, 0, 0, 2, sorry, I put it wrong. 0, 2, 0, and 0, 0, negative 1. Is that an elementary matrix? Why not? You did 2 elementary row operations, not 1. You're only allowed to do 1 for it to be an elementary matrix. So no, that is not. Okay, very good. And we'll see their solutions are, yes, the first one was, second one not, the third one not, the fourth one was, the fifth one was, and the sixth one was not, because you did 2 operations. Very good. Now, elementary matrices are useful because they enable you to use matrix multiplication to perform elementary row operations as demonstrated in example 2. Okay? My question is, why would you do it this way? Okay? Except if you're using a program to do it, and it might be, well, never mind. Hopefully we'll see. Okay. All right. Here is an elementary, well, you tell me. Here's a matrix, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1. Question, is that an elementary matrix? what did you do? Exchange the first two rows. So this is elementary matrix E. We're going to multiply this by any old matrix A. Here's what it happens to be. 0, 2, 1, 1, negative 3, 6, and 3, 2, negative 1. Okay? Now, this is any old matrix A. Now, I probably shouldn't approach it this way, but I think I will. If you were trying to get this in row echelon form, what would be your first step? Exchange the top two rows. Okay? And what did you say this elementary matrix was from? Exchanging the top two rows. So let's see what happens if we multiply this matrix by that one. Okay? You know how to do your, or first, can you multiply those two? Why? They're both 3 by 3s. 3 by 3 by 3 by 3 equals a 3 by 3. You got it. Okay? And let's do that first entry. What would that be? Pretty easy. 0, 1 plus 1. Okay, it comes out being a 1, doesn't it? Second entry, or the 1, 2 entry. 2, is it? 0 times 2 is 0, minus 3. Okay. I was going to do 1, 2, but if you'd rather do another one, tell me. Say again? Negative 3 going across. Now, are y'all doing it, or are you just knowing what the answer is? Oh, okay. If you're going down, let's go down. I don't care. Okay. Across. Next. 6. Next. 0. Next. 2. Next. 1. Next. 3. Next. Second. 2. Next. 1. Negative 1. Okay. All right. Now, notice what we've done here. Here from here to here, we exchange the top two rows. Okay. Now here, have either one of you done much or any computer programming? You have. Oh, you did. Both of you? Okay. Is this a legitimate command to give to a computer? Exchange the top two rows. Really? Computers can understand that. Wow. Okay. Then this is really old technology here. Because back when I was programming, that's not something computers understand. You have to tell it how to exchange two rows. If, and you set up a, say again? You what? Yes, exactly. Okay. Yeah, and you can do it. Yeah, I agree. It can be done. But what I meant was, can you type into the program, exchange the top two rows? No, computers don't understand language like that. Okay? So what you have to do is if then else, and you can get it done. Okay? And that's, of course, you have to set up an array, right? A two-dimensional array. You know, two things, and then you have to step through one and step through the other and stuff. Now, people have already developed the programs to multiply two matrices. Those are the same no matter what you do it. As long as the sizes are right, you can do it. Okay? So rather than having to write a program to exchange the top two rows and do that. Since this is already done, just enter this matrix into that matrix, and it exchanges it. Because the computer does those calculations maybe a little quicker than we did. Okay, not much, but a little bit. Right? Okay, and that's already done. How to multiply? They have these algorithms in place. How to multiply two 3x3 matrices. Okay, so that's how you do it on a computer. Now, this is my perspective. I don't know if I'm right on this, but this is the only reason I can conceive, because guess what? Doing elementary row operations, I would just have gone from this to that just by writing them down. Not by multiplying like this, okay? This is longer, more awkward. It's easy, but it's so much easier just to flip the two rows. So my guess is, and this is just a guess, they do this because of computer programming. That's the easier thing to do there. Okay? I don't know for certain if that's true. Okay? Now, here's a matrix. And okay. 1, 0, 0, 0, 1/2, 0, and 0, 0, 1. Okay? Is that, what kind of matrix is this? What kind is it? Second? This is an elementary matrix. Why? You multiplied the second row by 1/2 of an identity matrix by 1/2, and you got it. That's it. Exactly. Now, here's a matrix. 1, 0, -4, 1, 0, 2, 6, -4, and 0, 1, 3, 1. And I will take something back. Something we do later is going to require the use of elementary matrices. And I guess this may be something, but again, it's the only time we use it that I've run into is in this section, just to show how we use these. Okay. Now, first, what kind of matrix is this? It's just a regular old matrix. And we can call that, like they love to call it, A. Okay? Is there anything special about A? The only thing special about it is it can be multiplied by a 3x3 matrix. Why? Because this is it's a 3x4. It's not a square matrix. It will never be an elementary matrix. So why? It doesn't matter. We're multiplying. Oh, let's forget about this a minute. What would be your first thing that you would do to that matrix if you want to get it in row echelon form? You got the 1 with zeros below it. So that's good. Okay, you'd love to have a 1 there. Now, there's two ways you could get it. What are those two ways? Say again? Exchange. You could have done that. They've chosen not to. What's the other way? Multiply by 1/2, which is exactly how you got this elementary matrix. So let's see what happens if we use that elementary matrix to multiply this, which you can do. Well, you didn't tell me. Can you multiply those two? And if you do, what will you get? You'll get a 3x4, because a 3x3 by 3x4 is going to give you a 3x4. Absolutely. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. You don't have to do this. I just find it useful for teaching. Okay? Then what? Okay, the first row stays exactly the same. Have you done the math, or are you just saying that? Yeah, good deal. All right, and you said the third row stays the same? You're absolutely right there, too. I don't know if I believe you. No, I mean, of course I believe you. Okay. All right. But when you do the 2-1 entry, what do you get? You get a 0, really. Okay. A 1? A what? 3? -2. Which is exactly what you would have gotten if you multiplied the second row by 1/2. Which would have been so much easier to multiply row 2 by 1/2. But you would have had to program the computer to say, now you do this. Whereas all you say now is multiply that. Just call up the predetermined, what do they call that? Function, or there's another name. You call up can't remember. It's been so long since I did any programming. But you called it, yeah, and that would give it to you. Okay? Good deal. And we got the same thing they did. So, let's look at one more. What's that? I'm sorry? Okay. My hearing is so bad. I heard it coming back. Oh, yes, you never get out of it, do you? Okay. I have taken C++, but I know I've done programming, so I know that's what it does. All right. 1 0 0, 2 1 0, and 0 0 1. What kind of matrix is that? How? Why? How did you get it? Of an identity matrix, 3 by 3 identity matrix, by 2, and add it to the second row. Yeah, it is. Now here's a matrix. Here's a 1, 0, -1, and here's a -2, -2, 3, and here's a 0, 4, 5. Okay, that's just any old matrix A, right? But it is a matrix you can multiply by that elementary matrix because it was a 3 by 3. This is a 3 by 3. When you multiply those, you get a 3 by 3. And let's multiply. Second, it stays the same. 1 0 -1. Very good. Next. 0. -2. Okay. I didn't do it. Let me do it. Okay, that'd be a 0. Yeah, -2. Is it 1? Oh, yeah, okay, -2 plus 3. -2. Yeah, plus 3. Yeah, it's 1. You're right. Sorry. Next. The third row stays the same. 0, 4, 5. Okay? Now, was this what you were doing? You were supposed to be multiplying. Oh! I wondered how you were doing it so fast. I wonder you told me to be the same. What we're supposed to have been doing in all these is multiplying the matrices. So let's see what we get. Here's your 1. 0. 0, that gives you a 0. -1. Okay? Next row. 0. plus 3 is 1 plus 0 is 1. Okay? This would be, got it? No. 4. Okay? Yeah. That's how you're supposed to. I was wondering, how is he doing on that fast? Okay. You were doing row reduction. You're supposed to be doing that so you get the same thing. Okay? And that's the key. Okay? So if you're doing programming, and there's other reasons too. We'll see another reason later. I'd almost forgotten about it, but yeah, we will see it. But again, next time is the only time that we use it, but it says another reason. Okay. All right. In each of those 3 products, in example 2, you are able to perform the elementary row operations by multiplying on the left by an elementary matrix. The next theorem, stated without proof, generalizes this property for elementary matrices. Okay. Before we do it, here's a remark. Be sure to remember that this theorem to multiply on the left by the elementary matrix E. This text does not consider right multiplication by elementary matrices, which involves column operations. So let's keep it on the left. So let E be an elementary matrix, and since not everybody's here, and I'm not sure they got books yet, let me write this down for everyone. E is an elementary matrix. Okay? Now what does that tell you? If I say E is an elementary matrix, immediately what comes to your picture in your mind? Square matrix. Got to be square. Okay? And it looks an awful lot like an identity matrix with one little change. Only one. Okay. Okay. E is an elementary matrix obtained by, I can't write, performing an elementary row operation, elementary row operation on they're using M now, not N. Okay, I'm sure there's a reason for that. No, I'm not. Okay. If that same elementary row operation, I'm going to shorten this again, ELO, elementary row operation, is performed on an M by N matrix. Why they were doing N by N's before, now it's M by N's. It doesn't matter, they're just numbers. Oh, I'm sorry. Maybe this is the reason. Not on an M by M, but an M by N. Okay. Just like we did before. Okay. Matrix A. Okay. Then the resulting matrix, I can't write. Resulting matrix, what size will it be? It will be in M by N as well if you multiply an M by M on the left by M by N, M by M on the left by M by N on the right, you're going to get an M by N. Okay? I forgot to write it down. M by N matrix A. Wait. I'm sorry. I'd already written that. Okay. Lost my place. Then the resulting matrix is given by the product EA. Okay? And that product EA will be the same as if you did that same ELO, elementary operation, on the M by N matrix. That will be exactly the same. But it has to be on the left, multiplying by that elementary row elementary matrix on the left. Most applications of elementary row operations require a sequence of operations. For instance, Gaussian elimination usually requires several elementary row operations to reduce a matrix, row reduce a matrix. Now that's Gaussian, not Gauss-Jordan, but Gaussian. This translates into multiplication on the left by several elementary matrices, one after another after another. Boy, what a long way to do it. The order of multiplication is important. The elementary matrix immediately to the left of A corresponds to the row operation performed first. And we'll see that in example 3. So I think I'll clean the board. All right. This one I don't have to have my work studies there. Okay. Find a sequence of elementary matrices that can be used to write the matrix A in row echelon form. Now they didn't say reduced row echelon form, row echelon form. What's the difference between reduced row echelon form and row echelon form? Okay, yeah. On both of these forms, you have ones down the main diagonal, as far as you got a main diagonal, or they may step or whatever, but you got the first non-zero element in any row is a leading one, okay? And zeros below those leading ones, okay? Reduced row echelon forms also has zeros above those leading ones, okay? That's the difference. All we're doing is getting them below the leading ones, okay? So find a sequence of elementary row operations, elementary matrices that can be used to write this matrix A, 0, 1, 3, 5, 1, negative 3, 0, 2, and 2, negative 6, 2, 0. Okay? We want a sequence of elementary matrices that can be used to write this matrix A in row echelon form. What would be the first elementary row operation you would do? Exchange the top two rows. So what elementary matrix would you use to do that? Did he use the right size identity matrix? Did you? That's what I'm asking. You said no. Yes, you did, because it's a 3 by 3 multiplying by a 3 by 4. So that is legitimate. And I'm not going to write A, okay? Can you tell me what the answer will be? One, negative 3, 0, 2, 0, 1, 3, 5. See. Now, if I were doing this by row reduction, I would have, at the same time I exchanged these two rows, I would have divided this one by 2. It's so much easier. We're having to use elementary row operations. We may not do that, but it sure seems like a good choice. In fact, no, we wouldn't. What's the next thing you will do? Okay, go ahead. Okay, so you said negative 2 row 1 plus row 3 is going to be the new row 3, right? How would you write that in elementary matrix to do that? And, oh yeah, 0, you're right. 1. Right? Okay. There's your elementary. So this we'll call E1. That's the first one we use. This one we'll call E2. Okay, and we're going to multiply by that matrix here. So I'm just going to write it here just to keep from having to write so many times. And what does that give you? Oh, you have to take it off. That pumper doesn't work. And then yeah, that's what I have to do. Thanks. Yeah, you don't have to get it back on if you don't want to. It's a pain in the neck. Okay. 3, 5. Now you do the work. You can go and do it the way you want to. I know what you're doing. 2, -4. Okay. Do we have it in row echelon form yet? Why not? Or multiply by 1/2 or divide by 2, yeah. Okay, so your next elementary row operation, E3, that elementary matrix, I'm sorry, would be what?
1, 0, 0, 0, 1, 0, 0, 0.
Oh yeah, right. I'm sorry.
1/2.
1/2. Okay, I was getting ahead. Okay, you're absolutely right. And then when you multiply that by this matrix, you will, and you're really supposed to multiply, you'll get what? Yeah. You'll get 1, -3, 0, 2, 0, 1, 3, 5, and 0, 0, 1, second, -2. Okay, there you have it. That is in row echelon form. Not reduced row echelon form, row echelon form. Okay? You use these elementary matrices to get there. Okay? Okay. Now, I actually thought they were writing them this way. I wasn't paying attention. They wrote them, they reduced using elementary row operations, but then wrote the elementary matrices off to the side. Now, let's combine some stuff here. Okay? We started with matrix A. We wound up with a matrix here, which we're going to call B. Okay, I'll write it right now. This now is B. Okay? Now, I wish I had my old program that would work so much better than this one. But here's what I'm going to do. I'm going to write E3 down here. Okay? The reason I want the space up there. So I'm going to erase it here. So I wrote it first. Okay. Now here's what we just did, if you think about it. This matrix B here, we got from starting with matrix A, and then on the right, multiply it by E1, and on its left, we multiply by E1, on its left, we multiplied by E2, and on its left, we multiply by E3, and that gave us matrix B. Okay? And then they're going to go back and do the same things we just sort of did. We cheated and did them quickly. but they did. If you go back and do them, starting with the right, and working your way left, you see how they got it there in the text, okay? You first started with A multiplied by E1 on the left. That result you multiply by E2 on the left, and then that result you multiply by E3 on the left, and sure enough, that's how you got B. Now, that means that A and B are row equivalent, because all the operations you did were elementary row operations, so they are row equivalent. So here is then a new definition for row equivalent. We've had this before. Here's a new one. Definition of row equivalence: let A and B be M by M matrices. Same size, not necessarily square, okay? Okay, matrices. Matrix B is row equivalent to A when there exists a finite number, in other words, a countable number of elementary matrices EM, E1, E2, E3, ... up to E sub K. Yuck. I get to talking faster than I write and then mess up. Okay. Up to E sub K. Now this has nothing to do with M or N either one. It's just however many steps you needed, however many elementary row operations you needed, that many elementary matrices, such that, okay, B is equal to EK times EK minus 1 times EK minus 2 ... times E3 times E2 times E1 times A. Okay? You just put them in reversed order. Okay? Because the elementary matrices, the first one multiplied by this first, that gave you like size M by M matrix. Multiply that by the second, by the third, by the, keep going until you got B. Okay? That's another definition of row equivalence. You know for section 2.3, the last section, that not all square matrices are invertible, right? Okay? Every elementary matrix, however, is invertible. The identity matrix is invertible, and every elementary matrix you get from that is invertible. Okay? Moreover, the inverse of an elementary matrix is itself an elementary matrix. Now that's something new. The inverse of an elementary matrix is an elementary matrix. So here is theorem 2.13. Okay? If E is an elementary matrix, and we know what that means, right? Then E inverse, number one, it automatically exists because all elementary matrices are invertible. So E, the inverse of E does exist and is also an elementary matrix itself. Okay? Now, this next part I don't find intuitively obvious. Okay? So pay attention to it and focus on it. Okay. I'm going to do one elementary matrix, or you tell me if it's elementary matrix. 0, 1, 0, 1, 0, 0, 0, 0, 1. Is that an elementary matrix? Yes. How did you get it? We inverted row. They put row 2. No, row 1. Okay. To row 2. Yeah. That's how we did it. Now, the inverse of that matrix, E1 inverse, any idea what that one would be? The same elementary matrix. The inverse of an elementary matrix that you got from exchanging two rows is exactly that one. Because if you do that to this one, you're going to go back to the identity matrix. And that's what makes it an inverse matrix. Okay? So those two look identical. If that had been the first and third row, that would have been the first and third row. This would have been the second and third row, that would have been the second and third row. They are identical. They just undo themselves. Okay. Now, what if this was your elementary matrix, E2? Well, you tell me, is it an elementary matrix? 1, 0, 0, 0, 1, 0, negative 2, 0, 1. Is that an elementary matrix? Yes, it is. Okay. Now, how do we get it? Okay, and that gave you the new row 3, right? Good. Now, does this matrix have an inverse? We know it has an inverse. It's an elementary matrix. It will have an inverse. What is the inverse of that one? Say again? 1, 0, 0 is going to be the same. 0, 1, 0 is going to be the same, but what's going to be the next one? How about negative 1/2? No, you're right. No, I was wrong. We're both wrong. Okay. Positive 2. I was thinking the next one. No, 2, 0, 1. Okay. Now, if indeed these are inverse, if that is indeed the inverse of this one, we know this one has an inverse. It's elementary matrix. We know all elementary matrices have inverses. If that is the inverse, what's the product of these two going to be? What's the product of any two elementary matrices? I mean, any two inverse matrices? Identity matrix. Isn't that what makes it? And yeah, right? Go back, okay? Let's see if this works. So that would give you 1 where it needed to be. How about this? That would give you 0 where it needed to be. That gave you 0 where it needed to be. Wait. Yep, that gave you 0 there. Yep, that gave you 1 where it needed to be. That gave you 0 where it needed to be. Okay, here's where the proof of the pudding comes. Negative 2 plus 2 is? 0. Good. Zero. Yep, sure enough, that produces elementary matrix. So that is the inverse of this one. So in general, anytime you multiply any row by a non-zero element added to another row to get its inverse, you would multiply the same row by the opposite additive inverse and add it to the same row, because that way you'll get that. Okay? Here's a third type of elementary matrix. Let me use the same example they do. 1, 0, 0, 0, 0, 1, and 0, 0, 1 half. How did you get that? Is the new row 3. Right. That is an elementary matrix. It's guaranteed to have an inverse. And what would be the inverse of that elementary matrix? 1, 0, 0, 0, 1, 0, 0, 0, 2. Let's see if that works. You know, I'm not going to do the first 2 rows. I know what they're going to. No, I already wrote them. You let me get away with this, didn't you? Whoops. I miswrote that one. Okay. Right? Okay. Now, what would happen if you do? I'm pretty sure this gives you the right thing. That gives you the right thing. It's just this. One, yes, that does give it to you. Okay. So, I guess what I should have done here was this would be row 1 and change to row 2. Same operation produces same element. Those are elementary, or inverses of each other. Okay? This one would be 2 row 1 plus row 3 is the new row 3. It just multiplies by the opposite number. Okay? And the third one would be 2 row 3 yields the new row 3. Okay? So when you're changing 2 rows, exchange the same 2 rows. When you're multiplying a number by a row and adding, multiply the additive inverse by that same first row and then add it to the same second row. Okay? When you're multiplying one row by a non-zero constant by a row to get that new row, then multiply them by the reciprocal of that constant times that row. Okay? So, good deal. And it says try using matrix multiplication. We'll check these results. We sort of did. Okay? The following theorem states that each invertible matrix can be written as a product of elementary matrices. So I guess I'll write this down because not everybody's here and they may not have a book. Okay? Square matrix A, okay, is invertible. Okay, here's something new. If and only if, that symbol represents that, or IFF also represents it, or if and only if represents it, it can be written as a product of elementary matrices. Square matrix is invertible if and only if it can be written as a product of elementary matrices. Okay? Now, that adds to a growing list of what is required to be a invertible matrix. They all have to be square. You cannot have a rectangular matrix be invertible. It just can't happen. Always a square matrix. Okay. The first thing we ran into is that if you row reduce it with the identity matrix, augment it or adjoin to it, then you're going to get the identity matrix multiplied by the inverse. Okay, that was one. When you do a row reduction on it, you'll wind up with a diagonal of all ones. Okay, reduce row echelon, reduced row reduction, then you get identity matrix. Okay, We also threw this one in. We haven't done it formally yet, but we did it with 2x2s, that if the determinant is zero, is not zero, it's an invertible matrix. Here we have another. If a square matrix is invertible, if and only if it can be written as a product of elementary matrices. It doesn't say how many, but it will be a finite product. Okay? Now, they do a little bit with the proof. I don't think we're going to have time to do that. I would say read through that. It's really not that bad. But there's two steps. You have to prove it one way and then prove it the other way. Okay? And we will do example 4, which illustrates the first part of that. Okay? Find the sequence of elementary matrices whose product is the non-singular matrix A. I'm going to go on and erase this, I think, just in case I need the room, because these things do take a lot of room. So here's your matrix A. -1, -2, 3, 8. Now, can you do a real quick and easy test on this and convince me that is invertible? What would be the easiest thing to tell whether it's invertible or not? Especially since it's a 2x2. Say again? You think it is? I think it is too. How can you prove it to me? Real easily. Say again? Okay, yeah, don't do anything to it except find this determinant. -1 times 8 is -8 minus -2 times 3 is -6, minus the -6 would be +6. -8 plus 6 is -2, and that's not 0. If you can tell immediately what the determinant is and it's not 0, then it's invertible. If it is 0, it's not invertible. It's singular. Okay. So yeah, we know it's invertible. So they told the truth. Okay. Now we want to find a sequence of elementary matrices whose product is this non-singular matrix. Okay? Okay. Now, how you do that? Okay? What would be the first step you would do to make, to row reduce that matrix? What would be the first step you would do? -1 times the first row. So that would produce a 1, 2, 3, 8, right? How did you do that? -1, row 1 is the new row 1. Okay? Now, its elementary matrix that did that same thing, E1, would have been what? Say again? I don't think so. -1, 0, 0, 1. Okay. Now, okay. Now, they don't do it now, but I'm going to do it. What would be the inverse of that matrix? Of that one, this one right here, the E. -1, 0. Let's see if that works. Okay. Here's 1. 0 plus 0 is 0. Sure enough, that makes the identity matrix, so yeah, that's the same, okay? What we did was multiply just like we did before. Before, what we did, multiplying the top row by a non-negative zero, a number, -1, to a row, row 1, giving you, then we multiply the reciprocal of that, which was -1. So that's why it looks the same, but we multiply by a reciprocal, okay? Now, what's the next thing you would do here? Okay. Okay, let's do the row reduction. 1, 2, yeah, -3. I'm going to write it over here. -3 times row 1 plus row 2. Okay? What would that give you? 0. Say again? 2. Yeah, I couldn't hear you. Okay, 2. Okay, so our E2 here was what? 1, 0. -3, 1. And what would have been its inverse? 1, 0. I could have done that one. Okay. 3, 1. You're right. 3, 1. And you get that by, I mean, you could check that easily by multiplying 1, 0, that's 1, 0, 0, that's 0. -3 plus 3 is 0, 0, 1. Yeah. Okay. And we don't have time to do the rest. Yeah. Okay. These things take too long. All right. We've got down to there. We're going to start here on the third step here. And we'll just write down what we have from that point and go. Okay, homework exercises. We got decent way, but not all the way through. Do any of the odds 1 through 7. Do 9 or 11 or both. Do either 13 or 15 or both. Do 17 or 19, no, any of the odds 17 to 21. I think you can do either 23 or 25. And you can hold off there because that's what we're working on now. All right, good deal. And we'll pick you, well, I'll see both of you later this afternoon in different classes, but I'll see you. Good deal.